Better or worse?
Facci cosa?
So, good afternoon, guys. So this is your Dropbox folder. You have two new files. The first one is this one. So radar imaging, geometry, and waves. I just changed the file name, and so this is the file that you already read, but I just wanted to change the name because it is more clear. This is the new file, and this radar imaging signals and system part 1 is what we are about to see today. So before we start, we saw a MATLAB code in the last lecture concerning Doppler and waveforms. Any questions on that? Okay, so super clear. Okay, this is amazing. Okay, so today we're finally starts. Oops, no, I need another. So today we are starting to see radar imaging. So finally you will understand why this course is called radar imaging and not just radar signal processing. Because today we will start to form images based on microwaves. Before we start, your next homework will be assigned next week, maybe Monday, maybe Thursday, but next week. And it will be about radars and radar imaging. So let's say that today and Thursday will be very important. But let us just get started. And so, just to summarize what you already know, this is the scheme of the receiver. So you receive a signal at radio frequency. This is a real valued demodulator. So this is what happens in the real world. You are modulated by cosine, sine, and then you have the low-pass filter, and this is how you form your complex signals. And this is the expression we saw many times during the last lectures. Of course, okay, and so this is the delay and phase. Of course, we prefer to use the complex representation, so we just imagine that we transmit a complex signal, and at the reception, all we have to do in this way is to just counter-rotate its phase, and so we end up with exactly the same signal. we did talk about localization in one dimension. So basically we send a short pulse. In this case, this is just a rectangular pulse. And we can say that two targets appear as two distinct peaks as long as their distance is, the difference of their distances from the radar is larger than the pulse width, okay, scaled by the speed of light, of course. Is it really pulse length that matters? No. This is what we saw when we talked about the matched filter. Indeed, what counts is the length of the pulse after compression, so after matched filtering, which is basically the inverse of the bandwidth. And so, if you send a very long chirp, for example, this is what you get after post compression. And so your range resolution depends on the bandwidth, more bandwidth and finer resolution. So far so good. This is something we saw already, so these slides are just summarizing this old concept. And then of course, when you have multiple targets in the same range cell, then you have interferences, which can be either constructive or destructive. And so basically, this is a scheme that helps you visualize what is the resolution cell in the real world. So just imagine that you are transmitting this radar this way, and so you know that all the targets within the same interval of distances from your radar will go in the same pixel. And so in this pixel you have just this car, in these other pixels you have the mixtures of all the three canopies and so on. And so this is what you see. This is the signal from the car, and this is the signal from the interference of all the elements within the three canopies. And this is it for localization in one dimension. So from now on, we will be talking about localization in two dimensions. And this is a slide that was presented already, I think, the first time we met, so about 1 month ago. Now, this is the geometrical principle. So, flying a radar along a straight line means that you can measure the distance from the target to all the points on the line. So, this means that the target is bound to lie on these intersections of all the spheres with the radius that you are measuring, so with the radius that the radar tells you, and the center of each sphere is on the trajectory. And so if you intersect all of the spheres, what you end up with is a circle. Is this circle here, so it's a circle which is orthogonal to your flight trajectory. And whose radius is the minimum distance from the target to your trajectory. So it is this distance here. So basically, geometrically, without even talking about microwaves, radars, just geometrically, you know that if you fly a radar on a straight line, what you will is the capability to say that the target is somewhere on the circle. So, the question now is how to form an image. This is just a point and radius and so. How do we form an image? Now we take a step back and consider a problem which is known in signal processing as direction of arrival. You might have seen this with Spagnolini. You, no?
Not all, depends who follows.
Okay. Anyhow, direction of arrival is a famous topic in signal processing, and the aim is to know the direction of arrival of a plane wave which is impinging on a planar array. So basically, you have an array of many antennas, and imagine that for each antenna you transmit and receive a monochromatic wave. So monochromatic means no bandwidth. So we have no range resolution at all here. We are just emitting a single tone. Before you make confusion, this is not written here, but it is intended that I transmit and receive with this antenna, then I transmit and receive with this other antenna, and with the third antenna, and so on. So each antenna here is assumed to receive only the signal transmitted by itself. So this is not a minor system. And so the received signal after demodulation, we are transmitting a single tone. So this is our transmitted signal. After demodulation, we get a signal whose amplitude is proportional to the square root of the radar cross-section of the car. So this A car, here you have the radar equation in here, and whose phase depends on the distance and the weight, of course. Now let's put some numbers. The distance is just geometry, and so you can, if you assume that your array is at 0, then this is the expression of your distance. Of course, you can approximate this distance, or rather, you can approximate the variation of the distance along the array by virtue of linear expansion, and this is what you get. So you can simplify the expression of the distance as a constant term, which is, let's say, the distance from the center of the array, times the sine of this angle, times the difference between, let's say, times the position of each sensor with respect to the center of the array. This is, of course, valid when this distance is much, much larger than the array length. This approximation doesn't make sense if your array is longer than the distance from the target. But let's say that if your array is smaller than the target is far away, this makes sense. So basically, if the variation of the distance is linear, then it means that we can assume that a plane wave is arriving on the array. So, what do we know about the direction of this wave? Well, under the planar wavefront approximation, we can approximate the distance in this way. So, as a function of the angle and the coordinates along the array. Then this is the expression of our received signal. So you see you have a term that just depends on the radar equation. Then you have, this is a constant phase, and this is the varied part of the phase. And you see that this phase variation is equivalent to a complex sinusoid whose frequency is given by 2 over the wavelength times the sine of the angle. So basically, along this array, you have a spatial frequency given by this expression. So at this point it is easy, no? Since you know, so how do you detect the frequency? The frequency of a wave. So you have a complex number for each sensor. So in this case you have 6 complex numbers. You want to know the frequency, the spatial frequency of the wave. What you do? You can call me and I will ask you for a lot of money to tell you the right answer for
We can measure the phase difference.
you can measure. Okay, this is interesting. We are saying, can you read if I write here? Okay, so we are saying that with this experiment, what you measure is a complex number per antenna. Okay, and this complex number we are calling it S of n, and this is more or less equal to a complex number, so A times the constant phase times a phase ramp whose frequency is equal to, whose frequency is connected to the incidence angle. So if we know the frequency, then we know the angle under which the target is seen. Your colleague is suggesting to take a look at the phase variation between any two antenna pairs. This is okay. So if you take the phase, let's say S n plus 1 times S n complex conjugate, this is equal to 2 pi times f of x, or times delta x. Delta x is the space in between the two. So if you take the phase and you divide it by 2 pi delta x, then you know the frequency. Okay, is this optimal? Is this optimal against noise? This is the question for those who take the course of Umberto Spagnolini. Is this optimal concerning noise? Can you read it?
Yes.
Who says yes? Who says no? Okay, good. So the first thing to be noted is that it cannot be optimal because you have in this case 1, 2, 3, 4, 5, 6 complex numbers. So your data is built by 6 complex numbers, and you are just using 2 numbers. So for sure it is not optimal. Huh? It can be shown that if you assume that this is contaminated by white noise, then the best estimator of the frequency of a plane wave is to take the peak of the Fourier transform. So if you want to estimate this frequency, and I am writing here, what you do is here we have fx. Let's say, just to use the same notation as the last time, let's call this fx0. So this is the frequency corresponding to the true angle of the target. Then what you do, then you form this new signal S of fx. As the Fourier transform of your signal. This is the sum over n. What you end up with? So this is a function of fx. So you are trying to all the possible spatial frequencies. No? The last time we say we try all the possible positions and velocities. This time we say we try all the possible spatial frequencies. So it is exactly the same. What is the result?
Periodic function.
Periodic function, fine. And which periodic function? This is a Fourier transform of a this is a complex sinusoid, right? So this is the Fourier transform of a complex sinusoid. This is a complex sinusoid at frequency fx0. It's an impulse, but of course you are not summing over an infinite number of arrays.
So
No.
two pulses. Two pulses.
Why two? Why two? So I'm doing a Fourier transform, right? This is the Fourier transform, which is made in the discrete domain, because I have just 6 elements. So there is a sum here, not an integral. Huh? So the Fourier transform of a complex sinusoid is a delta, right? But this is done not from minus infinite to plus infinite. This is done over a fixed length. So the Fourier transform over a fixed length is what?
The convolution with a cardinal sign.
Cardinals.
And the delta,
And so the cardinal sign.
which gives a cardinal sign. So the result is a cardinal sign. What is the position of the peak? fx0. So the position of the peak is telling us which is the true frequency of the target. And this is optimal if you assume that your signal is contaminated by white noise. This is optimal. This is a maximum likelihood for those who are studying estimation theory. This is a maximum likelihood estimation of the frequency of a target, of a sinusoid. So you just do a Fourier transform, and the peak tells you the frequency, hence the angle of the target. How wide is this pulse? So the question is very important because Of course, if you have two targets that are positioned at the very similar angles, then you want to know if these two targets will appear as two different peaks or just a single peak. So it is important to know how the width of this peak, because you want to know what is your capability to resolve two targets at two different angles, exactly like in range. How wide is this?
Depends on the length of the array.
Yes, with which low?
The inverse.
Yes. This width is 1 divided by the length of this array. So let's say this is A, this is 1 over A. And then, as someone said, we also have ambiguities, because this is done in the discrete domain. So this is sample. And so when you do a Fourier transform of a discrete time signal, then you get ambiguity, you get replicas. So you also have a replica. At which distance?
The distance of the antenna.
Of a fix? No. Multiple of what?
Of the inverse of the distance of the antenna.
Exactly. So if this is the space in between the sensor, the replica comes at the inverse of the distance. You may want to notice, maybe you know already, that this fx is a spatial frequency. So it is not measured in hertz. This is the unit of this frequency is meters to the minus 1. So spatial frequency. Excellent. And this is solving the exercise for you. So you just do a Fourier transform, and what you end up with is a beautiful peak, which is telling you what is the frequency of the curve. Your frequency resolution is the inverse of the length of the array. Okay, well, A is the array aperture. Oh, sorry. This is called in jargon aperture. The array length, we just call it aperture of the array. Okay, here take care, because you might have ambiguities depending on the sampling of the array. And okay, so here is a case where two targets are correctly resolved. You see, you have these two targets at different angles, and so you get this is the peak of the curve, and this is the peak of the tree. Of course, take care, because you have ambiguities at 1 divided by the spacing between different elements of the array. These, in the radar jargon, are called either ambiguities or ghosts, because they appear as real targets, but they do not exist. So how do you pass from spatial frequency to angles? Well, it is a non-linear relation, so you have to invert this one relation. Of course, the angle cannot go, cannot be larger than 90 degrees. So imagine that this is the antenna array, so you are sensitive to target. Let's say this is 0, this is 90, this is minus 90. What I forgot to say is that if a target is behind you, then you cannot know it. So let's say that a target at this angle or at this other angle will appear exactly at the same position. And this is an intrinsic ambiguity of the system, which, if you like, we say that we are just localizing the target along a circle. So let's go back for a second. We say that what we are doing, so what we can do is to localize the target on this circle. So the target can be here, 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 which also means that the target can be in a certain position or at the opposite position. And you just don't know. But if you assume that you, let's say, if you limit your analysis to half space, then your imaging is not ambiguous between plus and minus 90 degrees. And so in this interval, you see that the frequency corresponds to an angle. If you assume that the angle is, let's say, within plus minus 30 or plus minus 40, this relation can be approximated as being linear. So you will just substitute the sign for the angle, and it is even easier. And your angular resolution is, of course, if you take the differential of this form, then you end up with this equation for your capability to resolve two targets at two different angles. This is super easy, no? So you have the frequency is twice the wavelength sine of c. So the differential of the frequency is 2 pi. The differential of the sine is cosine times delta psi, and from here you get this expression for the resolution. So, let's talk now about localization in two dimensions. We say that if you have bandwidth, then you can resolve the target based on the distance from the radar. If you have an array, then you can localize the target based on the angle under which they are seen from the radar. So if you just put these two together, then you can have 2D localization capabilities. So how does this work? Imagine now that each element on this array is emitting a radio frequency pulse. So first this one, and this is the signal that you get. Then this other one, and so the signal is slightly in a slightly different position because you have a different delay. We have a bandwidth now, right? So these are short pulses, and you can see the position. And so this is the data that you have. So your data is a function of two variables. T is time, as always. And in this case, tau, this other variable, is the time when one antenna is operated. In the radar jargon, we call it slow time. And so let's say that this is t and this is tau. Here. So this is a cartoon. This is a real data. Of course, a simulation done in MATLAB. But so this is the matrix, which is called the raw data matrix. And you see for each row, I have a compressed signal. And so you see here how this matrix looks like. The difference between the maximum and minimum delay of these signals is called range migration. Well, you should measure this in meter, of course. So the migration means how much this pulse is moving across different antennas. And for the time being, we will assume a simplifying. We will assume a simplifying assumption. We will assume a simplified system where the bandwidth that we are transmitting is narrow, which means that the temporal duration of each of these pulses is much longer than the range migration. You see the difference. In this case, the different pulses, so the peaks of the different pulses are on different columns. If we say that these pulses are very large in time, then we can say that all we have basically is just a single column. And why we do that? Because it will help us understand how to focus this data easily. So, this is what we have now. This is the expression, this is the mathematical expression of our signal, assuming that range migration is negligible, which again means small aperture and small bandwidth, and under the plane waveform approximation, which means small aperture. So, you see the same delay for all the signals, and then this is the constant phase terms, and this is the varying phase terms. This is a raw data matrix, slow time and fast time. You see here this is the amplitude, of course, and so you have here at least 1, 2, 3, 4 targets. You see, this is a constant amplitude, constant amplitude, constant amplitude. In this case, you have these variations, and we will see why. If you want to focus this data to form an image, all you have to do, after what we have just seen concerning the problem of the direction of arrival, is to take the Fourier transform of these methods, of the complex methods, of course. And you see that in this case, all of these lines get compressed to single point. So each bright point here is telling you that there is a target there. you can notice that we have 1, 2, 3, 4, 5 targets. So this simulation was done assuming 5 targets. You can also see now why this is not, why the amplitude here is not constant. It means that these 2 targets, they are at the same distance from the radar, and so their signals get mixed in the raw data matrix. And so you have that constructive and destructive phase interference phenomenon that we discussed. And so you have that the signal goes from the peak to, so goes from maximum to minimum, you see, continuously. This is more or less it. Basically, in this case, you are forming a signal in the domain fast time and spatial frequency, which is perhaps not yet an image, meaning that an image is something that you would like to represent the space as you perceive it. But of course, it is easy to convert this image, for example, from fast time and frequency to range and angles. This is a simple interpolation. All you have to do is to read this image at the coordinates. So this is the correspondence between time and distance, and this is the correspondence between frequency and angles. And so you end up with the same image in distance and angles. If you like, those are polar coordinates, because one coordinate represents the distance from the center and the other the angle. If you like, as I do, to work in ground coordinates, then all you have to do is to resample this image at this, assuming this equation. So this is the image in distance and angle. The distance is given by the square root of the sum of the squares of the coordinates, and the angle is the arcotangent of the ratio between the 2 coordinates. And so this is your image in the ground coordinates, x and y. A thing that I did not mention, this is not just a peak detection. So we are not doing this just to see the position of some target. You also have a third information, which is the amplitude of this target. Of course, this amplitude is connected to the radar cross-section of this target. And so you can say that your radar image is a map of the radar cross-section of the target. So what you see here is just the spatial distribution of the radar cross-section. So let's say if you take a photo, what you see is the spatial distribution of the radiance of each target, more or less. If you do a radar imaging survey, what you end up with is the spatial distribution of the radar cross-section of the target. So it is a different, you are measuring a different quantity using a different principle, a different system, but you generate an image as well. Very important. We saw here different projections. And so this is fast time and slow time, fast time and spatial frequency, distance and angles, or x and y. Yes?
When you talk about fast time and slow time, you mean that the slow time is the time in which every antenna is transmitting its pulse, while the fast time is the time to the signal for the signal to get to the target and then come back?
Yes, let's say the fast, yes.
Okay.
The fast time is the time, as we have treated it so far in previous lectures. The slow time, if you like, you can also substitute it with the antenna position. So slow time just means that at time 0, this antenna is operated. At time, I don't know, 1, this other antenna is operated, and 2 and 3. You can substitute with the antenna positions.
Thank you.
Really doesn't change. Okay, so what is very important is the resolution, meaning what is the geometrical size of these dots here, or in other words, what is your capability to resolve different targets based on their distance and angle from your radar. Well, it doesn't change. We say that you have a range resolution which depends on the inverse of the bandwidth, and you have an angular resolution which depends on the length of your aperture. If you